Okay guys, I'm going to do my best to give a quick overview of the second half of Module 4, especially for the few of you who weren't able to be in class this week. Okay, so we're going to start off on page 143 with handling the exceptions in ionic compounds. So basically just talks about how there are exceptions. In group 4A, there's germanium, tin, and lead are exceptions. And this is the basic reason because of this is because they can become more than one ion. And so when you're naming them or when you're figuring out what the structure is, you need to keep this in account, okay? So it's never going to be 10 chloride. If you have 10,4 chloride, the reason why that's important is because it tells you that 10 is going to have the +4 charge, okay? If you have 10,2 chloride, that's going to tell you that 10 has the +2 charge, okay? So the way I do this, if it says write the structure for 10,4 chloride, is I write 10, and then you give it the +4 charge. Chlorine, you can see on the periodic table, is in group 7A, right there. So if it takes on an electron to have the ideal configuration, it's going to have a -1 charge. So I just have a negative there. You could write -1. It's fine. And then remember the rule. You crisscross them. So it'd be SN1. And then you just drop the 1. And this would be your answer. Okay. Now, if I were given this, I need to also be able to get to this. If I was given this, what's the name of this? You should be able to see that it's 10 chloride. You would do it in reverse. You would say, okay, well, there's 4 here, so that means the S10 has to be a +4 charge. You know this, you work backwards and you can get this, okay? Same thing for 10,2 chloride. You know 10 is going to have the +2 charge. Chlorine, sorry, I keep saying chloride, but chlorine has a negative, and then you just reverse them, so it's going to be SnCl2, 10,2 chloride, okay? For your test, you need to be able to do both of those. Go each way for them, okay? So let's do another one. What is the chemical name for the ionic compound CuCl2, okay? So I know that there's 2, right? It really looks like this. Couldn't really type it up like that. So I know that it's going to be copper 2 because of this 2 down here. I already know from doing these up here, chlorine is a -1. So when I write, you reverse them. So I just know that this is going to be, you do the name of the first element. Remember your rules. So copper, you have to have 2 to show which ion it is, right? And then you end with your ide name. So instead of chlorine, it's chloride. Okay? What's the chemical name for PbO2? It should be written like this. Okay? So this is a little bit trickier because you know that oxygen, if you look, it's in group 6A, so it's going to have a -2 charge, but they show you your structure as this, okay? But you know when you do it that there's going to be a 2 here. So this has to cancel out, which tells you that this has to be a 4. Okay, you always write them in reduced form. So when you cancel that out and cancel that out, that gets your compound. So what does that mean? That means that it's going to be lead 4 oxide. Okay, lead is the first one. You use your ide name for your last one. Remember to put what ion it is. I hope this is making sense to you. Okay, so now we're going to talk about ionization energy and periodic properties. So ionization, I have it written here, but I don't know if you can see that very well. But ionization is the process by which an atom turns into an ion by gaining or losing electrons, okay? And ionization energy is the amount of energy that's needed to take an electron away from an atom, okay? So basically, each atom holds on to its valence electrons with different strengths, with various strengths. Some have really tight grips, while others hold on to them more loosely, okay? The tighter the hold on, I didn't spell that right. the tighter the hold on the electrons, the more energy will be needed to take their electrons away. This should make sense, right? Conversely, the looser the hold on the electrons, the less energy is needed to take them away. They're more likely to give them up, okay? So we can tell how tightly or loosely atoms hold on by looking at their electron configurations and the periodic table, okay? So if you go back to your periodic table, remember elements in group 1A, right down here, they have just one valence electron. All they need to do to be in their ideal state is to get rid of that one electron. So they are holding on to that one electron very loosely. They want to get rid of it. So the ionization energy for these atoms is low, okay? The elements in group 7A, they have 7 valence electrons. They want one more to have their ideal state. So they are holding on to their electrons very tightly. They do not want to give up their electrons. So their ionization energy is high over here, okay? So the periodic property in general is that the ionization energy of atoms increases from the left of the periodic table to the right of the table. So as you go from this way to this way, the ionization energy increases, okay? So magnesium, right here, has a lower ionization energy than phosphorus, okay? Because it increases as you go this way. And just for reference, a periodic property is a characteristic of atoms that varies regularly across the periodic table. And we're going to talk about several in this part of the chapter. Okay, so now that we know left to right, what about top to bottom? So in general, the ionization energy of atoms increases from the bottom of the periodic table to the top of the periodic table, okay? And I want to talk about why this is. So let's take two elements. Let's take oxygen and selenium, okay? So they're both in group 6A, and oxygen has the higher ionization energy because we know, because it talks about how it increases from the bottom to the top of the periodic table, okay? But I want to explain to you why that is. All right. So if we look at their electron configurations, I wrote them out for you. Okay. So the electron configuration for oxygen is right here. 1s2, 2s2, 2p4. So you know it has 4 valence electrons, right? Or I'm sorry, 6 valence electrons. That's why it's in group 6A. And the same for selenium. It has 6 valence electrons. Again, that's why it's in group 6A. Okay? So both have 6 valence electrons. But the oxygen's valence electrons are an energy level 2. And the selenium's valence electrons are an energy level 4. Okay, so this is important. So you've got your protons and you've got your neutrons. And then you have your electron clouds, your electrons orbiting around, and your various energy levels. Okay? So basically, the valence electrons in selenium are further away than oxygen. They're in higher energy levels, so they're further away from the nucleus. Okay? So the selenium protons can't hold on to its outer electrons as tightly as the oxygen protons can, right? They're further away, so it can't hold on to them as tightly. So therefore, selenium has a lower ionization energy than oxygen, and that should make sense. Okay? All right. Let's work through another example really quick, just with these properties. A chemist needs to find an element that readily gives up an electron. Which one of these would suit her needs the best? Calcium, arsenic, or bromine? Okay, so you can see that calcium, arsenic, and bromine are all in the same column. Calcium is over here, where the other two are over here. Calcium is the one that's the most ready to give up its electrons and has the lowest ionization energy, okay? And you also know that just from looking how many valence electrons it has, also the trends that we just talked about. Okay. I'm not going to go through that other one. So now let's go to electronegativity and the periodic table. Okay. While the ionization energy focuses on the ease of forming positive ions or how easy an atom will lose its electrons, the trend oppositely to see how easily atoms take on electrons in forming negative ions is your electronegativity. Okay, and the definition is the measure of how strongly an atom attracts extra electrons to itself. Okay, and the greater the electronegativity, the greater an atom's desire is to become a negative ion. So ionization. Okay, remember groups 1A have one single valence electrons, right? Over here, they have one single valence electrons. So how great is their desire to take on electrons? Not much. They don't want an electron. It's much easier for them to get rid of one electron than to take on 7 electrons, right? They're trying to get rid of it. So their desire is low. But if you go back over here to group 7A, they have 7 valence electrons. How great is their desire to take on electrons? It's very strong. By taking on a single electron, they'll have an ideal configuration, and that's what they want. So the rule to remember in general is the electronegativity of atoms increase from left to right on the periodic table. Okay? Now, what happens up and down? What happens vertically for electronegativity? Well, remember, atoms toward the top of the table have their valence electrons closer to their nuclei, right? We just talked about this a minute ago. So atoms up here have their electrons closer to their nuclei because it's in a lower energy closer, right? So the attraction of an atom for electrons should decrease from the top to the bottom, because the further the valence electrons are from the nucleus, the less attraction the protons are going to have on them. Okay? So the other thing to remember over here, these noble gases don't follow this property because they already have an ideal electron configuration. They don't want to gain electrons, okay? But in general, the electronegativity of atoms increases from bottom to top, or decreases from top to bottom, however you want to look at it. Okay? So now we're going to go to atomic radius, another periodic property. Although atoms have electrons orbiting in all sorts of shapes, right? We talked about S, P, and D. And I'll draw this for you really quick. So the D is kind of complicated. It doesn't exactly look like this. And then you've got your P's, kind of the dumbbell shape. They have an overall spherical shape to them, okay? And because of this, it's possible to come up with an overall radius for each type of atom. And hopefully this is obvious, but the larger the radius is, the larger the atom size will be, right? So let's look at electron configurations from top to bottom on the periodic table. Remember what we just talked about. Atoms high on the periodic table have valence electrons closer to the nucleus compared to atoms lower on the table. So the lower an atom is on the periodic table, the bigger it is, right? Because the farther away its valence electrons. So the periodic property for this is, in general, the atomic radius increases from the top of the periodic table to the bottom, okay? Now, what about left to right or right to left? This may not be as obvious, okay? So, but let's think about it. When you move across the table from left to right, the electrons are filling up the orbitals within the same energy level or below. And what I mean by below is when you get here and then you start dropping into the Ds. But they start filling up their orbitals, right? So let's look at row right here. We have potassium, calcium. Let's look at this row right here. Well, you should see that as you move from left to right, the atomic number, what happens to the atomic number? Well, it increases, right? Right here it's 19, then 20, then 21, then 22. Okay, well, why is that? It's the number of protons is increasing, right? So as you move from left to right, you're increasing the number of protons in the nucleus. And that gives the nucleus more positive charge, okay? So then the nucleus will be able to exert more electrical force on the electrons within the same energy level. And they'll actually pull the electrons a bit closer because of that more positive charge. They're going to pull them just slightly closer, making the size of the atoms decrease a bit, okay? So this may not be as intuitive, but as you're going from left to right, the atomic radius decreases, okay? From right to left, the atomic radius increases, okay? So I hope that makes sense. It really centers around the concept of the valence electrons, where they are and what energy level they are. So that will make sense. Okay, so I put a little note here for me to draw. So if this was my periodic table, actually, I think I'm just going to say, okay, I've got my periodic table. So in general, your rules are the electronegativity and the ionization energy increases from left to right on the periodic table. They also, both ionization energy and electronegativity, increase from bottom to top on the periodic table. Now, the atomic radius is backwards. The atomic radius increases from right to left on the periodic table, and the atomic radius increases from top to bottom on the periodic table. Okay, so I want you to remember those trends, and in just a moment, I'm going to talk about Lewis structures. Okay, guys, I'm back. So now we're going to start talking about Lewis structures of covalent compounds, right? In the first lecture I did last week, we talked about Lewis structures of ionic compounds, right? So while ionic compounds are made up of both metals and nonmetals, covalent compounds are made up of only nonmetals, right? Now remember that atoms interact because they want that ideal electron configuration status. So if covalent compounds only have nonmetals and nonmetals only gain electrons, as you learned from the first half of this module, how can they form? How can they get ideal electron configurations if neither atom in a molecule will give up its electrons? Well, they share, okay? I also want to note that in Module 2, you learn that elements are made up of individual atoms and compounds are made up of individual molecules. There's a little bit more to it than that. There are some elements that aren't made up of individual atoms. They consist of identical molecules, and these are your homonuclear diatomics, okay? You will need to know these. You will need to memorize these, okay? Your homonuclear diatomics. Now, I want to be clear on this, that the homonuclear diatomics applies only for elements, okay? Not for individual atoms within a molecule. And so what I mean by that is, in just a minute, I'm going to list them out, but oxygen is one of them. So it occurs like this in nature. I'm not talking about, when we look at a water molecule, I'm not talking about the individual oxygen atom in this molecule, okay? That's not a homonuclear diatomic. I'm talking about how they exist in nature for elements, okay? And since you're going to need to know them, I feel like I should write them out. Nitrogen, oxygen, chlorine, fluorine, bromine, iodine, I think I already said that, astatine, and hydrogen. Okay, so make a note, learn these. These are all elements that are made up of homonuclear diatomic molecules rather than individual atoms. So when you see these, this is how you're going to see them. Nitrogen's going to look like that. Oxygen's going to look like that. There's two of them. These just aren't stable as single atoms, so that's why they're homonuclear diatomic. 5 of these are in group 7A. If that helps you learn them, great. So make sure you know them. Now we're going to take a look at Lewis structures of these, okay? So when I have fluorine, and I have 2 of them, let me turn back to my periodic table so you can see. Okay, so fluorine right here is in 7A. Okay, so it has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. And same for here. 1, 2, 3, 4, 5, 6, 7. Okay, so when I'm putting these together, they have to share electrons. That's what's going to make this work. So it ends up being a shared pair right here of electrons. And then 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Like this, okay? So everyone has 8 electrons. They're sharing electrons right here. This is a covalent bond. A covalent bond is shared pair of valence electrons that hold atoms together, okay? And this is the major reason why covalent compounds are different from ionic compounds, okay? The atoms in covalent compounds share electrons to form molecules, while the atoms in ionic compounds give and take electrons to form ions, okay? So right here, an ionic molecule is held together because of the positively charged ions. The cations are attracted to the negatively charged ions, the anions, right? So kind of like that. Whereas over here, there's an actual physical bond holding them together with their shared electrons, okay? And to show that bond, we use a dash. So whenever you see that in chemistry, that's showing that there's a bond there, okay? So let's look at Lewis structures and see how we can fit the atoms together for these covalent compounds. And I'm going to give you some rules. Let me write them out and I'll come right back. Okay, guys, I'm back. So I'm going to give you some rules for how to create Lewis structures of covalent bonds, okay? So number 1, you're going to count the valence electrons in the entire molecule by adding up the valence electrons of all the individual atoms, all right? The second thing you're going to do is you're going to put the atom with the most unpaired electrons in the center. If there's more than one of these types, you're going to put them both in the center bonded together. Third, you're going to arrange other atoms around the central atom and bond them with a single covalent bond. Fourth, you're going to fill in the octets of the outside atoms. And fifth, you're going to make sure the central atom has its octet. I know this sounds complicated, but let me show you what I'm talking about. So if we're going to do carbon tetrachloride, this is the one I used in class, I believe. Okay. So I know I have 1 carbon. Tetra means 4. So I have 4 chlorines. Okay. So I have a carbon and I have 4. All right. Well, carbon is in group 4A. It has 4 valence electrons. 1, 2, 3, 4. And we did chlorine a minute ago. It's in 7. Oops, doesn't matter. Okay, so count the valence electrons, okay? So my total valence electrons is, I have 7 here, 7 here, 7 here, 7 here. That's 28, and plus 4 is 32, right? Okay, then it says put the atom with the most unpaired electrons in the center. That would be your carbon. And arrange the other atoms around it and bond them with a single covalent. So that's going to be right there. Then you fill in the octet around. Okay, now, does everyone have 8 and is happy? All of the chlorines have 8 and they're happy. Carbon has 8, 2, 4, 6, 8. And then let's count and make sure we don't have more than 32, which was what we started with. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Perfect. So this is the Lewis structure for carbon tetrachloride. Okay, I hope that makes sense to you. What is the Lewis structure for a water molecule? Let's do that together. Okay, so you guys know water is H2O. Hydrogen, there's 2 of them, has 1 valence electron, and oxygen has 6. Okay, the oxygen has the most unpaired, so we're going to put it in the middle. We're going to single bond the H's, and we're going to fill in the remainder. Oh, what did I forget to do? I forgot to write down the total valence. Total valence electrons. Okay, so remember 2, 4, 6, 7, 8. It's going to be 8. So 2, 4, 6, 8. Oxygen has 8. It's happy. Now remember, hydrogen only needs 2, and it's happy. Remember? Because it's trying to get to helium, right? That's one of the exceptions. So here you go. Now, I think I said this in class too. This is correct. What about if I had written it this way? Yes, that would be okay too. As long as you have 2 hydrogens bonded to the oxygen, no more on the hydrogens, and oxygen having the rest, it's acceptable. Okay? Now let's look at slightly more complicated ones where we start having to use double bonds and triple bonds. Okay? So we've got oxygen. We know that oxygen has 6, right? We just talked about that a minute ago, and there's 2 of them. So our total valence electrons is 12. Okay, so how do we make this work where the oxygens are happy? Well, we put a bond together. But I don't have enough. When I take 2 away, 10 is not enough to make both of these happy. So I need to share another pair, okay? So 2, 4, 6, 8, 10, 12. I have 12 valence electrons. And then this oxygen has 2, 4, 6, 8. And this oxygen has 2, 4, 6, 8. So that's when you start putting double bonds into account, okay? So the other thing I want to mention is that a double bond is stronger than a single bond. It's held together more tightly. And a triple bond is stronger than a double bond, okay? So we can do this electron shuffling around and sharing as long as you don't add or get rid of electrons to the total valence number, right? This number needs to be the same here. You can't have more here. So if you're doing your structure and you have more electrons here, that should alert you that you're doing something wrong. Maybe you need another bond in there, you need a double bond, you need a triple bond, something like that. That should kind of alert you, okay? So let's look at a triple bond example, which is nitrogen. So nitrogen is over here in group 5A. Sorry, I didn't mean to take you guys for a spin. So nitrogen has 5 valence electrons. So your total valence electrons is going to be 10, right? So the way to make this work, remember you start and you, well, I already know that's not going to be enough, and I already told you it's a triple, so I kind of gave it away. So it's going to look like this. So each nitrogen has 8, 2, 4, 6, 8 for this one, 2, 4, 6, 8 for this one, because they share. And then all together, 2, 4, 6, 8, 10, 10 matches up, okay? So hopefully that makes sense for you. So let's work one more. Let's do the Lewis structure of carbon dioxide. So carbon dioxide, my carbon has 4, and you look at your periodic table to determine that. My oxygen has 6. My other oxygen has 6. So my total valence electrons that I'm working with is 16. Okay, so I'm going to take my carbon. It has the most unpaired. I'm going to put it in the middle and single bond it to my oxygens. Then I have to look and see how many are left. So I started with 16. If I take out 4, that gives me 12. That is not going to be enough to make my carbon and my oxygens happy. So I'm going to need to do double bonds here. So 2, 4, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16. Let's say I didn't know that. So let's say I went from having this, and I knew I was going to have to do this because I knew the numbers didn't right. Let's say I tried to do the rest, okay? So 2, 4, I tried to give this one 4 here, and then 2, 4, 6, so then I tried to give 2 here to carbon, and then I tried to do this. Okay, so everybody looks happy. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Okay, but here's where the problem is on that. If I count up electrons, I have 2, 4, 6, 8. Remember, there's 2 in each of these lines. 10, 12, 14, 16, 18. That tells me something's wrong. I have 2 extra electrons here. So I have to take these away and double bond here, and I'm good, which gives me this. 2, 4, 6, 8 for carbon, 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. And 2, 4, 6, 8, 10, 12, 14, 16, which is my total. Okay, so that's what I mean by if you're doing your structure, and then at the end of your structure doesn't match your total valence electrons, you have something wrong. Okay? Hopefully that makes sense to you. I think that's pretty much it for this lecture, unless you guys have questions. So I'm going to try and get this up so you can watch it. And please feel free to ask me questions.